Following on from the previous video, we are now going to try and prove the first part of the theorem. So what this is saying is that if the sequence converge to some c above 0, then these two will act in unison with each other. Meaning, if this diverge, then this will diverge. If this converge, then this will also converge. So let's say this thing here converges to some number. Let's say 5. 5 is above 0. So it's saying that because it converges to a number 5, then these two will act in unison with each other. If this thing here converges, and this thing here will converge. It's quite strange that because the limit is 5, then these two must act in unison with each other. Well, it may be strange when you first look at it, but if you think about it, it's not that strange. Because let's look at this. Let's just say this thing here converges to the number 5. Converges to the number 5, and let's say the series here converges to the number 2, then the denominator cannot diverge, because for it to diverge, then the denominator will get bigger and bigger and bigger, meaning that the limit of this thing will head towards 0, but it must head towards 5. So if the numerator converges, let's say converges to 2, then this thing here must also converge. It cannot get bigger and bigger. So let's say this thing here converges. So let's say the denominator converges to, let's say, 2. Then for the limit to be 5, then this thing can, the numerator. So remember, the denominator converges to 2. The numerator must also converge. It cannot get bigger and bigger. It cannot diverge. For it to get bigger and bigger and bigger, it will imply that this thing here will just get bigger and bigger and bigger. So in a way, they have to act in unison with each other. So if it converges to 5, the two must act in unison with each other. So let's start again. So now we're going to try and prove it. So let's say this thing here has been satisfied. So the limit of the sequence heads towards some sort of c, and c is above 0. So this thing here has been satisfied. So for this thing here to be satisfied, it would mean this. So for this thing to have been satisfied, it would mean this. So what this means is the sequence is heading towards some sort of c. It's heading towards some sort of c. So it must be. So remember, from the definition of limits, given any tolerance, for it to have a limit, our c must lie in between this band here. It can wiggle back and forth. You can even make the tolerance to be smaller. So it will beyond some sort of capital N, for all n beyond capital N, it must fall within this band here for any given epsilon. So for this to be satisfied, it will fall within this band here. So I can actually deduce this. I can actually say for all n above capital N. So for all n above capital N, I don't care about over here. Basically, this is saying I don't care about anything before capital N. So for all n beyond capital N, so I don't care about anything here. I'm just talking about this bit here. So this thing here must be less than this thing here. So here normally we would say this. It must be less than So this is saying if you get the sequence, take away the limit. If you get the sequence, take away the limit, it must be less than half of c. So c from here to here, half of c is here. Okay, so this is half of c, and this would be c plus half of c. So it must fall. So this thing here must be within. It can wiggle back and forth within this band here. I don't always have to do half of c. I can do, let's say, a third of c. So this is so c is from here to here. So I can use a third of c. So I can actually say, well, a third of c would be here and maybe here. So it must be here. So earlier was half of c would be here. It must wiggle within half of c. But I can use a third of c. I can use a quarter of a c. So c is here. Half is here, a quarter would be here. So from here to here. So it must this thing here must it can wiggle back and forth within this band. So basically, I can deduce this. Okay. Well, we could use a fifth of C. We could use a seventh of C. Let's just use half. So now we've got this thing here. So for the absolute value to be in between, for the absolute value to be less than this, I can actually say it must be between minus this thing and positive this thing. So these two are really saying the same thing. So I'm just translating this. So now you can add C equally to both to add C. So add C here and then add C here. So this is 2C over 2. That would then give you 3C. And then add C over here. That would then give you this. Now times Bn to both sides times Bn. That would then give you this. Now once you get to this stage, you can actually see that as Bn. Once you get to this stage here. Hang on. Once you get to this stage here, you can see that if this has been satisfied, then if this thing here diverges, then this thing here diverges. If this thing here converges, this thing here will converge. You can see that. So suppose this thing here diverge, meaning this thing here gets bigger and bigger, meaning this thing here gets bigger and bigger. Remember, C is a constant. C is when it converges to some sort of limit C. C is just a constant. Earlier we used an example of the number 5. It's just a constant. So you can see that if this thing here diverges, then because this is a constant, then this thing here is going to get bigger and bigger. It will head towards infinity. If this series diverges, because this is a constant, this will also diverge. So AN is trapped in between these two, so AN must also diverge. Once you get to this form here, if BN converge, then because this is a constant, then this must converge. If BN converge, this is a constant, so the whole thing here must also converge. Well, AN being trapped in between the two must also converge. So when you get to this stage here, you can actually see that the two must act in unison with each other. If this thing converge, then this must also converge. If this diverge, then this must also diverge. So now we've actually proved the first part here. These two are quite straightforward, right?